Thank you. Thank you, Chair. Good morning, everyone. My name is Xiaoning Jian. Possibly my student, he some visa issue couldn't come, but I think I can handle it. With Dr. Tian's introductory presentation on this micro machine 1/3 composite, I want to move one step further to look at the micro machine 1/3 composite array. First of all, I will take a look at this background and motivation of this work, and then we look at the array design and fabrication, characterization, and we'll come to the summary in the future work at the end. Atherosclerosis disease is still the leading mortality in the United States or developed country. If you look at the fresh, new, healthy coronary vessel, you look something like this with the lumen area, with the interstitial media layer clearly seen. But later on, when usually come with aging, I see in the normal artery, I gradually have this early atheroma, have some of these atheroma developed over the years. You will see, form all kind of different kinds of plaques. Some of the plaques you have a very thick cap like this, and with a small lip pool or the calcified. But some of them you have this really very thin fibrous cap with a very large lipid pool as kind of a vulnerable, very dangerous plaque. So here, this is conventionally there are, as Dr. Tian just presented, and ultrasound has been commercialized, being used in this area by looking at the morphology of this coronary vessel structure. And nowadays, although there are many vendors out there for the IVUS catheters, but those are two are still main type. One type is the Boston Scientific one, or it's a representative. There are a few more players coming to the market recently. What that is, they have we call this mechanical rotational IVUS catheter. They have a single element 40 MHz. Some of them have 45 or 50 MHz. It rotates at high speed to get the cross section of coronary beam mode image. The other one is a Volcano 20 MHz 64 element circular array. This is Volcano itself also released that I think it's a 45 MHz rotational one too. And this is both of them have been in market for years. More recently, a lot of research work still going on in this area. You have heard one, and you're hearing the other one. There are many more in this session. We'll hear more. Basically, we want to look at the dealing with two problems. One, we want to see going to the high frequency, get a better resolution. That's one. The other is how we can identify those vulnerable plaques. That's people have working on the different ways. One of this one I mentioned my work first. This is the one we have been working on with NIH support. We want to work on this acoustic angiography, this dual frequency enhanced, contrast enhanced ultrasound imaging. And that also we target for the vascular imaging so that we can get some information about the vulnerable plaque. And we also work on this dual frequency micro machine 1/3 composite. We're trying to see whether we can get some tissue harmonic imaging in this area with IVUS. And Dr. Zhou and Dr. Shan's group, they have have been in this area high frequency ultrasound for years, and they recently work on this multi-frequency IVUS. With the idea, we want to look at high frequency, high resolution. At the same time, if you can take a look at this vulnerable plaque identification, would be great. So when we go to the high frequency, there's a reason because we want to get relatively short pulse so that we can get better resolution. And then look at the sensitivity. Mostly we tie them with material properties. Dr. Tian just has a really thorough rationale on why we need to look at the different materials, look at different structures, right? So here I just put a few of them just for the comparison. You look at PZT, 5H, you look at polymer, you look at PMN-PT thickness mode, and then you look at this PMN-PT composite. So you can see, compare the KT acoustic impedance and the D, and also the dielectric constant will be an important part. So basic idea is we want to look at really a high coupling coefficient, and when the acoustic impedance get lower, that's favorable, and overall we want to get really high frequency, high sensitivity. So high frequency, high sensitivity is the goal. And with those coming in mind, we want to look at the single crystal once we composite. We want to get a very high frequency, and also I want to look at array design. You have with Volcano 20 megahertz array, they do have a advantage in terms of the operation. When we look at interesting, you look at some of the cardiologists, relatively younger cardiologists, they prefer the one without too much of mechanical rotation. If you look at the old days, a lot of people still think, oh, that's very, rotational one really good, image is better. The only thing for the rotational one, image is, it's not comparable. There's some downside is because the 20 megahertz array. So that, our goal here is one look at using single crystal 1-3 composite, or also want to look at higher frequency, which is the 40 megahertz IVUS array in this case. And this is why we want to use 1-3 composite, how we fabricate it. And we when the time I was with TRS, we reported for the first time in 2006, this conference in Vancouver, I still remember. We reported this process and reported first time the micromachine 1-3 composite, and later on CTG or then HC materials has been very successful by looking at different with different pattern, deep edged PMN-PT 1-3 composite. And this is a slide with this one. It's a collaborative work with CTG. We got this 1-3 composite from them. This here is the key coupling and acoustic impedance. Be happy when Dr. Chen said most of the coupling coefficient, greater than 0.7, but not everyone. We got one. He just get the really the poor property one to me. That's kidding. We got one. It's still pretty good. You get 0.65, almost 0.7. Comparing with when Dr. Joe asked about 0.72, that's for PZT, relatively lower frequency, and this is getting to 40 megahertz for PZT. I doubt you can get as close to this. So with that material ready, and the next thing we do look at these 40 megahertz array design. We want to basically look at it's not the go back. Yep, it's not yet really a 3 French. It's close to the Volcano design. We want to get the OD about 2.2 millimeter. We're able to get the pitch about 140 micron, with each beam weighs about the 80 micron. Elevation we have 800 micron. So we got 50 element, and with the active layer, we got this about 28 micron PMN-PT 1-3 composite, and the matching layer here we use the parallel coating layer. It's about 10 micron, and the backing now have a E-solder silver epoxy. And we did, with this, we want to do, first we do a film model to check what is the single element impulse response. And with the property listed here, with the active material, matching material, and the backing material we just went over, should be able to see some of the, with the single element, we should be able to design as this. We should be able to get the center frequency around 40 megahertz and bandwidth around 70%, minus 60 dB fractional bandwidth. And the next thing is we mount the flex circuit over there, and then we wrap them around a Kapton tube. It's an 11 gauge tube, and then we also solder these to a PCB board so that we can get the wire connected for the acoustic test. And for the single element power cycle test, we look at the previous scale model and what we really got. It's close enough. We get about 39 MHz in the minus 6 dB fractional bandwidth, about 65%. And we get the power cycle amplitude about 150 millivolt. Again, this is just the material we got, and we did the prototype and not necessarily optimized. And the next thing that we did is this is one of the things we have been very limited because of the imaging system available. We don't have that 40 megahertz or 50 megahertz sonic system. What we did is here, with that array, we individually pause them. And then also we receive this echo, and then we just do the each one with the through the whole circle. So we get each A line we put together to form that phantom image. What we had is we put two phantom wires, 50 micron in diameter, and position them With two phantom wires, we position one about 2.5 millimeter away from the transducer, and the other one is about 5 millimeter away from the array. So this with the A line, we have I think a couple of broken elements, so we're able to see these phantom wires clearly. With the beam width about 70-80 micron. But we do have really poor lateral resolution at the point, and said we don't have that high frequency system available. If any of you have that capability, we'll be happy to work with you to move this forward. Summary: we're able to develop a 40 megahertz 50 element IVUS array, and we did the element acoustic characterization and the phantom wire imaging test to verify indeed with our actual resolution is possible. And we do need help with a high frequency system for more imaging ex vivo and in vivo tests. This project has been supported by US Army Congress Project 1 and also by R1 and partially by this ACBIR collaborated with Playtech. With that, I will stop here. Thank you. I'll be happy to take your questions.